Hello everyone, my name is Taro Arikawa from Chuo University in Japan. I would like to talk about development of disaster prevention platform in coastal resilient community. This shows the coastal protection policy in Japan. In 1956, Sea Coast Act was established to prevent by using the seawalls and breakwaters. This figure shows the time history of the number of casualties due to the storm surge and tsunami. In 1896, Meiji Sanriku Shrine was attacked in Japan, and more than 20,000 people were died. And after this Sea Act Coast was established, not so many casualties were there due to the seawalls and breakwaters to prevent the tsunami and the storm surge. But in 2011, East Japan earthquake tsunami was occurred, and more than 18,000 people were died. This video shows the damage of the Otsuchi town, and in 2011, here the seawalls with 5 meters high above the ground height was there, but the tsunami were overflowing and destroying the buildings and houses in the hinterland. So that after the 2011 Tohoku tsunami, Japanese government submitted the guidelines for the reconstruction with the concept of the multiple defense by using the multiple hazard levels. And the level 1, we set the 2 levels of tsunamis. Level 1 tsunami is defined as high frequency but low impact, with a return period is almost 100 years. And we use this tsunami to construct or to design the seawalls and breakwaters. And the other tsunami is we call the level 2 tsunamis. The return period is several 100,000 years, so much higher than the level 1 tsunami. And we use this tsunami height to plan the evacuation planning. So we are making the very resilient community by using the hardware countermeasures and software countermeasures. And now we are developing such a system for supporting the evacuation. At first, we are building a flooding database for the heavy rain, storm surge, and tsunamis, and create a database for the evacuation route and evacuation places, and also building the database on the people behaviors in case of the evacuation. And these kind of the smart evacuation guidance system to determine where and when to evacuate. This is the main engine to create the database for evacuations, for supporting evacuation. We call this numerical system is large-scale, multi-physics integrated calculator for storm surge and tsunamis. So we can calculate from the epicenter to the town. So that means the propagation, how to propagate, how to inundate, and how to destroy. And also these kind of numerical simulations are connected with the evacuation analysis based on the multi-agent simulators. The validity of the model is demonstrated by using the case study of the Kamaishi breakwaters damage in the Kamaishi Bay. Here is you can see the breakwaters in the mouth of Bay. The southern part is almost 700 meters, and the northern part is 1,000 meters. And the water depth is almost 63 meters. So this is the deepest breakwater all over the world. But the breakwaters almost with 30 meter high, 30 meter wide, and 30 meter long. But these breakwaters were washed away or tilted due to the tsunamis. And we reproduced by using these calculators, and from the epicenter to the area of the breakwaters, and you can see the breakwaters was washed away but due to the tsunamis. And we are checking from the videos analysis, and we verify this validity of this validity by using this case the damage case. Next, I would like to explain the evacuation supporting system. At first, we are making the database of the tsunami inundation by using the numerical calculation. And when the earthquake would be occurred, based on the epicenter location and the magnitude information, we are selecting the scenarios and set the earliest tsunami arrival times. And after this, by using this information, we select evacuation route, and of course, does not encounter the tsunami. According to the predicted tsunami arrival time, we assess the tsunami encounter along the evacuation route and construct a method to select the shortest evacuation route. And at first, this system search for the shortest evacuation route of the nearest evacuation places based on the predicted tsunami arrival time. And by using this prediction, if the evacuee encounters a tsunami, then does this system search again for the shortest evacuation route of the next selected evacuation places. And after that, the system judge the evacuee does not encounter the tsunami, then this system shows the evacuation route and that does not encounter the tsunami. So we call this system is tsunami encounter avoidance route selection method. We verify this numerical supporting system by using the local case. Here is the Ots town, and we are checking the evacuation route and the evacuation places, and these kind of numerical conditions, and by using the 2011 tsunamis. And we are checking the effect of the avoidance system in 2011 tsunamis. At first, the incident tsunami waves by using the 2011 tsunami, and after that, we are checking the evacuation avoidance system. This video shows the demonstration by choosing the shortest route for evacuation. Evacuee encountered tsunami if he select the shortest route. But by using the avoidance system based on the database, evacuee selected another route, even if this is not shortest route, but he doesn't encounter tsunami, and it is safe to reach the evacuation place safety. So this is the difference between the with or without the evacuation avoidance system. The left-hand side, this is the shortest way, but the evacuee encountered the tsunami. And the right-hand side, it is not shortest route, but he avoid the tsunamis. So this figure shows the effect of the avoidance system based on the database. And you can see these figures, and the dot line is the tsunami arrival time. So if the tsunami, when the evacuee ran away, as soon as the tsunami arrival, then the 68% reduced the mortality rate. So that is the effect of this system. Finally, I would like to show how to show the evacuation route, or how to support the evacuation route. This is now under construction, and we use the AR device to show the evacuation route and which is better route. I think you may know the evacuation AR device. This is the example of what is the AR device, and the AR can recognize the position of you stand, and to add something, and then you can understand which direction is okay. And we tested we applied to the local area, and this is the red line is the evacuation route. This video shows how to support the evacuation route by using the AR device, and he can recognize which direction is better to show by showing the evacuation by showing the AR device. We also applied to the storm surge and waves prediction. These are the system of how to predict the storm surge and the waves. And we conclude the 900 to 1,000 kilometer offshore from Japan coast, we obtained high accuracy both track and intensity. So the evacuation simulation will be connected with this simulation with this simulator. Then we can support the evacuation route or evacuation plan. And we apply to the heavy rain also, and this is collaborated with the Professor Yamada in the river laboratory, and we are predicting the real-time prediction by using the numerical simulation and the radar data. Then we support the decision making for evacuation by using this system. And also, we are considering the uncertainty of the damage of the embankment. This facility is we have in our laboratory, And this device is to measure the force of the water. And also, I think this system can be useful for not only for the research but also for the education. Okay, thank you for your attention.